Well, that's interesting. So the microphone was off. So we'll start again with microphone. You guys can hear me now?
I think it's on. Probably on the other one.
Did you switch it to the...
I can hear it.
But in the recording, it didn't go through, right? Okay, so I'll start again. Very quick recap. What we're going to do in this the fall semester is we're going to talk first about the S-domain, the Laplace transform, and what it's got to do with economic engineering. And afterwards, we'll be talking about analytical mechanics. So first, here's an equation. This room is full with engineers. What they do is they recognize, and there's the Laplace transform. So if you ask an engineer, I asked a random engineer, didn't work out so well for me. I thought he would be able to do it, but, you know, so they think of this as a Laplace transform, and they think of this S as a complex number, okay? And hence, this thing is also a complex number. This thing you think of as a real number, so you take real signals, you multiply it by this, and you get a complex number out of it. That's not typically what a physicist would do, and he would look at S as an imaginary number, so something that he can write like this, where omega is a real number. He thinks of that as the frequency, the same as we do, but he leaves out the real part of the frequency. Okay, this is where the word frequency comes from in our case. We started off with thinking of this as a frequency, and then we added the real part, and we still call it a frequency. Okay, so it's a little bit crazy to call this a frequency because it's not. It's more of a decay rate, but the terminology has stuck. And then they would recognize something that they would call the Fourier transform, and they get very excited about this, especially mathematicians. Also physicists doing quantum mechanics because they can analyze vibrations and all these things. And they don't have much damping in physics since quantum systems don't have any damping. It's a macro phenomena, so they can get away with using this. We'll find out that the Laplace transform has everything to do with damping in engineering. Okay? Now, so we got the mathematician, we got the physicist, we got the engineer, and you know, the joke always has at least a few of these people, we add an economist. Now, an economist, if you would look at that, what would he see, right? Now, none of you are an economist, but you got to get a sophisticated one, and what he will see is something that is called the present value of a cash flow. So what he does, he will think of this as a cash flow, so some payment at some moment of time. He will discount that with the time, you know, depending on when the time comes. He will add up all the payments since he has a flow. He'll get a number, and that's what he calls the present value. So unlike the engineer, who doesn't have any interpretation at all with the Laplace transform, it's just a trick, right, for him. This guy, he has a very definite interpretation, okay? Now, what this lecture is about is to solidify the engineering use of the Laplace transform as a tool to the interpretation that economists have, and then in economics generalize these tools that we have so we can apply them to economical problems. And you can use the Laplace transform and actually know what you're doing. All right? So notice that for the economist, everything is real. So this is a real variable, this is a real variable, and hence this is also real. Okay, so the present value of a cash flow is a real number, the cash flow itself is a real number, and the discount factor is also a real number. All right? For the physicist, everything is imaginary, and for the engineer, we have some kind of mix and match solution. So we have a little while to go in order to get this all right and start unraveling what the real part does, what the imaginary part does, and blah, blah, blah. All right? So the normal treatment of the Laplace transform in an engineering text will if possible, start off with the Fourier transform and then kind of extend it to the Laplace transform. And that's how a mathematician would do it too. Start with the Fourier transform and then push it over through something that is called analytic extension to the entire left half plane. So we are going to take a different approach. We're going to start with the real part of this thing. And I think that's the way Laplace originally used it, only the real part. He was looking at solutions of the heat equation, and there are no waves in that. So it's a first order differential equation, and there's no waves. So, and another thing Laplace was doing, he was solving problems with gambling. So he was a gambler, and it was very fashionable for gentlemen to gamble. And he calculated the moment generating function, which is also a real valued only application of the Laplace transform. So we're going to use that and then work our way back to the typical Fourier transform and the combination. Okay? So it's quite a journey, and it's a journey starting at a point that you usually don't start off with. So the problem with the engineering interpretation is that if you take I looked at a bunch of control texts, and I looked also at mine, old one, both while I was studying here and the one I got at MIT, and they don't really treat it very well. They just write down a bunch of definitions, you know, and then they'll say, all right, and this is the inverse transform, and they say, oh yeah, well, that looks difficult. You know, the great thing is you never have to use it because here's a table, and you just use the table, right? So then you say, all right, okay, well, that's nice to know. Just forget about this because I don't need it at the exam of why this thing works and what it does. All I need to know is to manipulate this table. Okay? You learn that and you do that. That's an accurate description of how I pass my exams, and it's probably an accurate description of what you are doing. So we're not going to do that. We're going to spend all our time, you know, figuring out what this thing is doing, and then I'm going to take for granted that you learn later on how to look through this table and solve problems, and then you can use that techniques in your economic applications. Okay? All right. So this lecture is all going to be about this one formula, believe it or not. Okay, so now forget everything you know about the Laplace transform and everything. Let's take a point of view that an economist might have. Now, if you go back to this thing, there's a couple of magic things happening here. And one of the magic things that is happening is this number E. Now, where did that number E come from? If you look at the history of the number E, it's usually claimed that it comes from finance. Okay? And then later it's used in engineering. But that's not quite true, because if you go a little bit deeper, you see that it was from geometry and it had to do with problems of quadrature of the hyperbola rather than the circle and everything. Okay? So we will take both approaches, but we're going to start off with the origin of the number E in finance. Okay? That was done by a guy called Bernoulli. And he named it in honor of Euler, I believe, who was also messing around with it a little bit before Bernoulli. So what we're going to do is find the origin of this number E first, okay? Then there's another magic thing in this thing, is that S is sigma plus I omega, and this I squared is -1, right? It's also kind of magic, all right? So the next lecture, we'll see how that magic number kind of comes in here and how you would have to interpret it economically, all right? And then by that time, you'll be able to figure out why this is the case, okay? So if you do that, this is a famous equation, and it combines all 4 funky things in mathematics in one formula. So E is funky, I is funky, pi is funky, and negative numbers is funky. So if you were a Greek mathematician, you wouldn't know what the heck this is about, okay? So this is also a little bit of a warning sign that this business of the Laplace transform is not easy, right? So there are entire papers written on the number pi. There are huge papers written on the number E and the number I. You know, all kinds of philosophers have talked about it. So we'll all have to cover all of this in order to understand this. So the weird thing about the Laplace transform that I find actually is that it's easy and not easy at the same time. So before I go on, let me just ask you, I know who is an engineer who actually solves engineering problems? Let me, I don't know, Rumer, let me ask you. Huh? So if just throw everything away, if you just said, if you had to explain somebody, what's the use of the Laplace transform in control engineering, what would you answer them?
Method of solving differential equations.
Exactly, right? And what does it do that it makes it so easy?
It transforms differentials into multiplications.
Yeah, and a multiplication is an algebraic operation, right? Yeah. So you get these differential equations and all this the complicated calculus, and you can just turn it into algebra, right? That's really the reason. And you don't really care about anything else. That's the trick, right? Now, this is not what so we'll get to this point too. Why is this the case? Okay, and why is it all going to make sense economically that you can do this and take a differential operator and do it in there? So the answer of the usefulness of this formula of the engineer is precisely that. It's just convenient because I can do all these problems with just using algebra. And we're lazy, we don't know much math, algebra is easy, so I can just do s squared, blah, 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 and I solve the problem, characteristic equation. All right? Huh? The economist won't say that, okay? When he says, what's the use of this formula? All right? He won't say that. He will say something like this. So I want to, at the end of the lecture, we'll at least be able to put those two concepts together and why that works, okay? Now, let's start talking about what an economist will do, how he would come up with this number E and how it came up. And this is the work, as I said, by Bernoulli. One of the Bernoullis, I never know who. They were apparently brothers, so, and they were both very prolific, so we got lots of Bernoulli stuff, but there are two of them, so you have to really divide it by two in order to get their exact. Now, I just opened up Investopedia, and they would just say something like this. So suppose you have a payment. I give you $1. Now, how much is that worth? Now, obviously, that's worth $1. I mean, you're giving me this now, right? But now that same dollar I'm going to give you a year later. Is that worth the same to you as $1 now? Obviously not, right? All kinds of stuff can happen in the meantime. You know, you may never receive this dollar, you may not be there, or the dollar may not be worth anything, or you have all kinds of stuff. We might have pay interest, or I don't know what. Huh? So either way, it's got to be lower. That's one thing we know. And it's going to be lower by some factor. So I'll take this payment, I'm going to multiply it by some number. Nah. I'm going to divide it by a number. What? So whatever this future payment is, I'm going to divide it by this number and say it's 1 year, then this year is 1, then this will be the present value. Now, how do you see that this is the right number? Well, what you can do, you can take the present value, what it's worth now, and what is it worth now is whatever it was worth today at this moment, and then you have to, what am I doing? You have to subtract, in this case, the discount rate. Anyway, I think I'm being a little bit confused here about it. It's worth a little bit less, and it's exactly this number. And if you take the discount rate, it's going to be bigger than 1. So if you work that out, that works. You can also take the present value, multiply it by 1 plus this discount rate, and you'll get the future value. Okay? This is a little bit easier to see. This is sometimes called the carry. Okay? So you have something here, then in order to bring it to the future, you have to pay an additional amount, which would be the interest rate you'd have to pay, right? Or something like that. So you get this plus the interest rate is the future value. I just turned this equation around. And then if I bring it not 1 year, but another year to the future, I'll get that the present value, I multiply it by this, I multiply another time, and I do that n times, and then I get this formula. So the present value is the future value, the 1 plus the discount rate to the power of the number of periods, okay? I thought it was totally obvious to me, and then I tried to explain it, and then I got myself muddled up. But anyway, I'm sure you guys are not as confused as I am about this. Anybody, is this confusing, or is this okay? Yeah? You guys see this, right? Okay. So you can write that as a change in the price. That's some payment you're going to make. And I'm just going to replace S by the discount rate, so it will just say this. And then I can define 1 divided by 1 plus S to be Z. And then I just get this, this statement here. Now, this you should recognize. I took the Z only to make it look like you're taking a Z transform of this one thing, right? So this is what you multiply a signal with when you take that Z transform. So here we have the first kind of connection is if you have a future value and you want to have a present value of any payment, you could use something like the Z transform and then sort it out like that, right? And then if you have an entire signal of payments, you would just sum over n. Okay? So there's already a direct connection between what they call discounting, where you could take a future payment and a present payment, and relate it to take it to the Z transform. So that's already pretty satisfying. So we made our first connection to engineering. Yes?
For my own context, what would discount rate be?
Well, so you take the present value, right? You multiply by 1 plus S, if this number is for 1 year, yeah. And you get the future value,
yeah, I get it.
Right?
What will discount rate be about?
What this will be?
Yeah, so numerical value. Yeah.
Oh, it depends. Say it's the interest rate, so then it will be 5% or something, right? Huh? It could be 100% too. Then you just double it. It doesn't really matter, right? Could be any humongous number, huh?
Could it also be negative because interest rates are pushing negative?
Yeah, no problem. You just put a minus sign here.
But then that means that
the future value will be lower. So the thing will be what, in contango or backwardation? I always get the two confused. Yeah, sure. All you're doing is taking something now and carrying it to the future. Depending on the carry, what you get for it, you're going to have to use positive or negative. Huh? Sure. Yeah. The usual case, what they look at is that you have positive interest rates or positive carries, and then you get this thing called normal backwardation, So you have to pay more for a future thing than for a present thing because you have to compensate somebody for the cost of carrying this thing. He has to pay all the storage and everything associated with it, all right? And with money, you can't really use it, so the convenience yield is something that will just have to be subtracted, So if you work your way through it, you will see that this is kind of a setup, right? Okay? So if you take a little bond graph where you have these things, you might come up with such a formula to calculate the present value. If you felt like calculating such a number. That doesn't have anything to do really with any variable of price or position or anything. It's just some kind of thing times something else, and we'll have to figure out what it has to do with that, right? Now, one of the things you can do, and this is what Bernoulli did, was, and this is kind of the brilliant move, okay? So now this economist or this finance guy, he's saying, okay, I receive a payment, I have an interest rate of 5% per year, say, so I receive a payment every year, boom, boom, boom. But you can do something kind of cool. You can say, all right, if you have $100, you'll get $5. But what if I pay the first of these $5, that's $2.50 after 6 months. And then you get the second one after another 6 months. So I divide up my total $5 into 2 increments of 2.5. Okay? You guys follow that? Actually, that's the way bonds work, treasury bills work. So rather, if they have an interest rate of 10%, they don't have this anymore, or 5%, they also don't have that anymore. They give you every 6 months a payment. So they are biannually compounding, okay? This is just the way it's done. They could give you a payment every quarter. That's what's typically done with other bonds. They pay every quarter. And they could pay every month, they could pay every week, you could pay every day. That's how it's done in your savings account, I believe. You accrue every day the interest, okay? I'm not sure. Huh?
Yeah, they do. My bank does that.
Your bank does that?
They pay only once a year, so they just collect it.
Oh, yeah, but they
for every
every day they collect it, right? That's right.
And then you get 5 cents at the end of the year.
Yeah, then you get 5 cents, yeah. But otherwise you would have gotten 4.7, right? Huh? Yeah. So this business is called compounding. And the rate at which you make payments during the year is called the compounding frequency. Now, if you get paid, I mean, in your bank, they actually reinvest it for you. You know, if you get paid this interest, you could put this back and let it grow at that same rate for an additional period, okay? So if you make that assumption, you're going to see that this factor 1 divided by 1 over s that you had here, 1 divided by 1 over s, of course I'm taking it here to the nth power, but let's just look at 1 year. You will have to divide the interest rate in k pieces, so you divide it by k, and then you have to compound that k times. So you have to exponentiate to the power k, right? Follow that? So Emil is getting a little bit more money because this thing is actually bigger than this thing, all right? That's easy to prove. All right? Then you can ask yourself, now what if I make that infinitesimally small? All right? Then I get the limit of k goes to, all right? Now what is that thing? Now if you calculate it, you can go do it. So you say that's this times this times this, k times. So you'll get a 1, and then you'll get s over k, but it's something, you can calculate that whole series, all right? And what you find is that it's equal to e to the e, all right, in this case.
No, e to the power s.
S, I'm sorry. Now you will find that, but Bernoulli didn't find that because he didn't know yet about the number e. All he proved was that this thing converges to some number that's an irrational number, all right? And he called that number e. If he put an 1 here, so he put it e, he called it number e to the 1, and that is e, all right?
Are the slides then wrong? Because on the slide you have e to the minus s.
No, because this thing is equal to 1 plus s over k to the minus k. So if this thing, then this thing, yeah?
Sorry.
So this is like, I mean, I'm only answering it because I myself got confused. This thing is 1 divided by e to the s, and that's, it's kind of confusing, I admit, because I was messing around with this too. I got it wrong. So you're making the same mistakes that I was making. Okay, so what Euler did was Bernoulli he defined this to be E. Okay, and nowadays we do the same thing. So normally it's done with the Taylor series. That's just this thing. That's just this thing expanded out. But many advanced texts will just use this this limit here as the definition of E. Okay, so we recognize it as E, but really you shouldn't. You should see that this is a way of defining E, what it is. All right, we'll find another way of defining it, and then we'll see that those are the same. But this is what usually people call the origin of the number E, and why it has to do with compounding. Okay, it's just what they got when you get a cash stream going continuously in. Okay, all right. So that's an important thing to realize, okay? And let it sink in you that these things don't come out of nowhere. You say, hey, I recognize this as E. No, the thinking goes a little bit different. You start off with something real that's happening in real time. And then you do stuff with that, and you make it finer and finer. You think, look, I'm getting tired of making it so fine. I'm taking that limit. Now, why would you get tired of doing that? Well, the answer is a little bit subtle. It's almost like you don't want to say in advance how tiny you're going to make it. So you want to give engineers a solution that will work for any discretization step. And that you do by taking this limit. And you can plug in anything you want, and it will always work. All right? That's the use of these limits. All right? Okay? So there we are. We have this number E. We found it. And then we can plug it in that other formula. The payment, I'll change it to, it now goes on time, so I'll change that to, so the delta P becomes F dt, right? I plug it in there, and then there you are. So this is the present value of a payment at time t, and the payment is Ft dt, okay, with this discount rate, okay? Right? Simple. Now, this is a simple payment. Now, this is the way things stood until Laplace showed up, right? This is all that Bernoulli and Euler did. And Laplace, he made the critical step, and that's the following. He started considering, now, one more step in between before we come to Laplace. All we did there was figure out what a single payment is worth. But now we have a whole stream of payments, okay? So all we have to do then is take this expression of a single payment of t and just add them up from 0 to infinity, okay? And we're assuming here that the 0 is now, and we're assuming here this is our horizon. It's infinitely far. Now, usually they're not, but it doesn't matter. We'll just say, get this sort of limit. Look, if I take it infinitely far, it will always be good enough for somebody with a really long horizon, you know, and if they're really worried about it, he can always like cut this thing off and set it equal to 0. So it effectively will always work. All right? So this is then the, if you plug in S and you plug in this f of t and you calculate this integral, you get this number V, which is the present value. All right? And this is where things stand in economics. Okay? This is where things stood in mathematics and engineering until Laplace took the critical step. It's really important to see this is a critical step because students get confused here. You know, what the Laplace transform is. And what you do is you kind of rewrite this thing this way. Now, so all I did was take this thing and pull it out of the integral sign, the way a physicist might write it, right? They'll put the dt all the way here, actually, okay? So nothing much, okay? But if I do that, I can replace kind of this whole big mess here by a little L, all right? And I can think of this as something, an operator, right, that is acting on this function in time and giving me this value, all right? But this operator is going to depend on this value of s, because if s is a different value, I'll get a different operator. So the whole operator has an argument with s, all right? So this is different, okay? This is a critical step, and it's very hard to make, I feel, conceptually, especially at the time that Laplace made it, because why would you think of an operator on a function? I mean, we have operators on numbers, you just multiply that by another number, then you have an operator on a vector, you know, there's a matrix. But this is a function. I mean, how is this a matrix? You don't know. I mean, you can think of it, some infinite dimensional matrix, but even that won't quite work, you know. So you got to kind of abstract away and see as this sort of a vector space of functions, and you put this operator on this function, and boom, out comes another function, which now has as argument this thing, s. All right? Okay? Because your t is gone. You just integrated it out. There's no way of recovering it, despite what some students want to do and put it back in. There's no way. All right? Huh? But the s is there. You can't get rid of it, right? And this operator is dependent on this s, and you can write it underneath here like this, but we really like to do it like this, okay? So now we have a mapping that takes a function out of some functional space. This is in some huge space. Usually they're called Hilbert spaces because they can be squared integrable, and takes it and puts it in another space, also some humongous space, H for Hilbert space, doesn't matter, right? It's a space where every point is a function, and it just does this mapping, all right? That's what you got to see. This is what's hard, because in those days, people didn't see that spaces could be bigger than three-dimensional. They just thought of space as being this three-dimensional thing. They couldn't see a vector space with a vector of length 5 that this lived in a space. That was just for them inconceivable, okay? Let alone a function living in a space, all right? So Laplace made this step, right? So it's a space, you can't even imagine where it is, but every point is this one function, and the Laplace transform takes that function and plops it in another one. Okay, this step has not been taken in finance. Okay, all they do is calculate a value, a present value. So this thing is really something more. It's the present value function, which is a function of the discount rate. And sure, think about it. I mean, if your discount rate is lower, you're going to have a different present value than when it's higher, right? When your discount rate is 0, you're just not discounting at all. You're just giving the stuff in, right? You're just integrating your signal out. Okay? If your discount rate is huge, you're only going to pick up a little small initial part of your signal. All right? Okay? But it's a critical step. We as engineers, they throw this in with one of these, you know, when you get your milk as a baby, how do you call those things? Huh? What? This bottle, yeah. So we get this thrown in. You know, as if we're babies with the bottle, and they say, here, we start the Laplace transform, they just write it down, and this is a function of s, and this is a function of t, and blah, 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 blah. Okay, look, okay, now go ahead, right? But, and I want you to realize that in order to apply this to finance, to cash flows, you got to see that this extra step can be now applied there, all right? Okay? So this is the first important message, all right? So when you have, if this is like a force, economic force, a want, you can look at this thing and it will give you all the, some kind of present value of all your future wants. If this is a flow, it will give you some present value of everything that might flow in the future, right? Huh? It's good to see that this is the present, right? Huh? That's the assumption here. You can't go back in time, all right? So if you compare this to what Newton does, he calculates momentum, but he comes from minus infinity to the present, and then he knows what momentum is, right? This is very different. You go to the future, right? Huh? So it's very different. There's only one point where they coincide, and that's the here and now. And So they're very different concepts. All right. I have a little bit more time before our break. So let's just at least first walk our way through the units, what happens here. So let me just write it down. We have this V of S, and it's the integral. And I just wrote an economic want here. And for now, we have the discount rate is just a real number. So we're really comfortable with what this says now. Now we start now, we go out to an infinite horizon, and we just do this business. And what that has to do with our circuit or our system, we don't know yet. We'll all find that out and how the transfer function is done. Right now, we're just going to focus on this, okay? Now let's take some Laplace transforms of some simple things. I'm going to start over with the commodity, where you remember we had a want, and that was measured in currency per unit per time. Huh? And the conjugate was the flow. The conjugate flow in your bond graph is units per time, okay? Now, what you're going to do is you're going to integrate this want. If this is the F, you just plug it in there, right? Huh? So what you're going to get is something, you see the time will fall out since you're multiplying by dt. That's right, because you're adding up all the payments over time, right? Huh? So you're going to get something in dollars per unit, okay? So that, I would say, is the per item value, right? So that's the total value that it might, the present value, right? So there's the present value per item, huh? Or per meter, or whatever you measure this commodity in, right? Okay? But I don't like to, you could call this the price. And in security markets, all these things are often confused. But I like to keep a price to be just a time domain concept. And here I just use V. That's why I didn't use a big P here too. Also because there's confusion with power, all right? Huh? So I like to think of this as a value, and you may think of the value as being a price, but it isn't really a price, because if you buy something on the securities markets, you don't really pay cash for it. You think you do, but you don't. You're actually exchanging one flow for another flow, right? Okay, we'll get to this later, okay? So never confuse this with a price as we defined it in the time domain. You can use the word price, but always be careful yourself that this concerns something else. The price is from minus infinity to if zero is now is exactly this thing, okay? And it's clearly a function of t, all right? The value, you go the other way from now to infinity, and it's a function of the discount rate of s. Right? It's a completely different thing. And you can't just write something like this. This is nonsense, okay? This is a function in the time domain. This is a function in a completely different function space. Why would these values be the same? You can't even rig the arguments to be the same. Now even that doesn't make any sense. Huh? All right? Now, you can also take the Laplace transform of the flow, right? So you will do the Laplace transform, how do I, the velocity of t, e to the minus st dt. What do you get? It's something that I would call the quantity, although Kuhn uses the velocity, the quantity. But for me, look at the units. It's going to be just the quantity itself, right? It doesn't have the feeling of a flow anymore. It's just... you're getting all these goods delivered in the future, all these eggs or whatever it is you're buying, and you're saying, well, it's just equivalent to, for me, to getting all this stuff right now. Now, of course, they go bad, but you're accounting for all of that in your discounting, okay? So it's an equivalent statement where you say this quantity is, to me, and this measure kind of that's the way I would measure the total amount, present value of this flow of the commodity. It's a little bit You have to get used to it a little bit. And the problem is probably that economists never take the present Laplace transform of something that's not denominated in cash flows, dollars per, per time rather than this. But I don't see a problem. Now you can just make the definition, and you just have to be a little bit careful that you give it a name that is representative of the problem you're trying to solve. Moreover, I think this is one of the things we want to do as engineers, like push this idea a little bit further so we can take Laplace transforms all over the place, okay? And we can do this type of frequency domain analysis. Now, I don't want to get too picky about the terminology. Kuhn uses one, I use another, you may use a third one in your thesis, but I want you to be sure of all these, very confident about all these distinctions, because they're subtle and it's easy to get lost because you call both a price, right? And then when you see these people talking, you've got to try to figure out, what does he mean? Does he mean a value or, So he may say something like, if you're at PwC, he may say like Kuhn is, may say, okay, the price of I buy this company for is I'm using, discounted cash flow measures, DCF method. And then they're just calculating a present value and they're claiming that is the price. Okay, but it really isn't. At least not from this definition perspective. Okay? All right. Now there's another analog, is a rotational analog. I didn't really analyze it too well in the lectures, and I had half a mind of doing it today, but I really didn't want to get bogged down on even more bond graphs. I gave a small lecture on it during, it was not really a lecture, a presentation during Rabobank, and Emil has been working on this. But in any case, you can make, this is the linear model where you just have mass springs and dampers, and this is the rotational analog, okay? So you look at, instead of linear momentum, you look at angular momentum, and instead of a velocity, you look at an angular velocity, okay? Now, then what happens is your one turns out to be this thing, and this is what's usually called the cash flow, okay? Now, you got to be careful again, because cash flows are used in two ways. First, by accountants in a cash flow statement. This is actually what happened. This is how the cash flowed in the past. That's a time domain concept. Accountants are in the time domain. But if you talk to business types or finance types, they talk about future cash flows. So what they want to do, they want to value a company. They don't care what happened so much as they care what's going to happen, because that's where the value of the security is in, the price they're willing to pay. Okay? And that they call a cash flow analysis, okay? It's interesting because even the Wikipedia article gets this right. If you look up cash flow, it will say there are two meanings, 1 and 2, all right? So I'm using this cash flow here, but with the caveat that this is not the cash flow, that is the kinetic energy, right? It's just another concept, all right? It's just confusing, but look, that's it. I mean, what do engineers do? When you take the Laplace transform of a force, you also call it a force. I mean, it's crazy, because it doesn't even have the units of force. It has the units of momentum. But you will just call it the frequency, the force in the frequency domain. Here, boom. Huh? So this confusion is there also for engineers. The only difference is when you're an engineer, you don't even know what it means anyway, physically speaking, what the Laplace transform is, so you won't get confused, since you're just like using it as a way to manipulate your differential equations and get the right results after you take an inverse transform, which you just look up in a table anyway. So you won't get into trouble, but in economic engineering, you have to think this all through, and you'll get yourself totally muddled up.
This is the same as torque and
yeah.
Both are in.
Yes. Torque and energy have the same units. Yeah, because energy is a force over some distance, right? And it's the in product, right, is actually a force vector in a product position. Let me Force vector in the product position vector, right?
Work in it.
That's the work, right? And then the torque, the reason it works is this is the cross product with the arm, right? The position vector. And they are not the same, but the units are going to end up to be the same, all right? So that's the example, but you got to see that this is energy, and this is, just because things are the same unit doesn't mean they're the same thing. All right? That's right. But then, you see, so this analog comes the closest to how economists may look at it, even in the terms, right? So you take the Laplace transform of the torque, and then you will get something that is just measured in dollars, and is not per item, right? And that's really what they would call the present value, right? Okay? Evaluated at a particular s, because as a function, they don't really do that. So you see, we've already pushed this idea of present value quite far, There's all kinds of new things are coming in. It becomes a very versatile tool, all right? Now, interest rates. Interest has got no units. You can also do this. What does the word interest mean? Now, there are a couple of ways to do this. You can say, well, the interest is the total interest I received over the period. That's more of a time domain thing, okay? So that's the total angle you made. But this is not how most finance people talk about it. They will call that the total interest received over the period, or total interest receipts, or something like that, right? When they say they have an interest in a company or interest in an account, okay? Accountants also use this term. You have an interest in something. So, for instance, when they are looking for who belongs the assets to, when they look at ultimate beneficial owner of something, they will say, he has a 3% interest, he has a 5% interest, How would they measure that? Well, they have some ideas behind it, of course, and some formulas. But what you could imagine is, what is the point of all these assets if it were not from the stuff you're going to get from it, okay? And how much are you going to get from it? Well, that all depends on what the interest rate is. So if you then look at the Laplace transform of your interest rate, that is your total interest that you have, okay? So intuitively, that's why I chose this word to be the interest. But again, now it's just up in the air. So every application you have to struggle a little bit to find the right terms that people use, okay? Are they using price here? Are they using that? Are they using such? Are they using so? In fact, you can wonder, when we have a supply and demand graph, it always looks something like this, right? Here's a velocity, here's a momentum, and then we do that. But you could even think of taking Laplace transforms on both sides here, and you're going to get another relationship, right? It probably won't, it's going to be an S in there or something. We'll see this later, and then this gets the feeling of a quantity demanded, right? That is everything that's going to be demanded in the future, okay? Very different feel. And what we've been interpreting this as, namely as this thing is just shifting over time and you're moving along over time. I don't feel economists are always that clear whether they are thinking of this in the Laplace domain or in the time domain. So I think when you do your applications, you've got to worry about it. We'll get to this example. Then we can be Joris Ladinois, and look at something like capital, like housing, and then, the want is this bad boy here, right? That only Joris can tell you exactly what it means. It's not so hard because he has this housing services that are, the items here are really the so many square meters over the year that you're providing, okay? And then you can take, the cool thing about that is that the flow is just the square footage itself, or square meterage. I don't even know how you say that in English.
But would this be only for housing, for example?
No, you can put labor here. You can put
but it's also years
capital.
spared in the one.
Yeah, of course, because you're doing something per year, right? So capital services are machine years, labor services, labor years, man years, I would say, man years or woman years or whatever, horse years if it's a horse doing the labor. Yeah, you can plug in anything. I just put in square meters because then I can give some names to it, what might be appropriate, right? So anyway, I don't want to worry too much about all of this, but just to give you an indication, when you start looking at the Laplace transform, be careful of the units. They do change, right? And you add a unit of time in the numerator and it just changes the whole feel of the thing, right? But then you can compare it to the integral of this one, but it's not the same. But it has the same units. There's something that's missed in all engineering analysis. If you take especially electrical engineers, they're always in the Laplace domain. They take the Laplace transform of the voltage. They'll just call it a voltage. So is it measured then in how do you measure a voltage? In volts? Yeah, sorry. I couldn't. I said, no, I don't know. I don't know. Huh? Yeah. Well, I have friends who are very good, and I said, I never thought of that, right? Huh? Yeah. I said, it's measured in volt seconds. Why would that be, right? Say, well, Laplace transform. Oh, yeah, well, I never thought of that. Oh, geez. Huh? You always look at it from a complicated point of view, they say. So, okay. Then what I want to do after the break is dive into some of these properties that you really know very well of the Laplace transform, final value theorem. I'm going to do something cool. I'm going to tell you where poles come from, and then I want to calculate some present values and just make this whole business come alive, that all these things you know how to look up and always forget again, right, just have an immediate meaning, all right? Okay, so let's take a short break. It's a little bit before 5. I have an ambitious program, so let's convene at 10 past 5, all right? Let's reconvene then, okay? Yeah.
The fourth slide.
Okay. Kijk eens wat de dingen. All right. Let's continue. We were here. What I'm going to you have all these different analogs. What I want to focus on, and the rest is just this rotational analog, where the force or the want is a cash flow. All right, this just makes everything easier. Otherwise, I have to talk about per item and do all this other stuff. All right, and it fits best with the use in economics. So the terms will all be comfortable. So the first thing I want to do is go through. These are the kind of tables. There's like 2 tables you guys learn. Is this one and that one. All right, those are the only 2 you use. And then maybe a little bit of this. So what I want to do, and these tables you just kind of learn it, all right, and then you don't really memorize it. You look at it. What I want to do is, with our present interpretation of what this thing is doing, why this all makes sense. Okay. So the first and the foremost thing is something that is called linearity of the Laplace transform. So remember, the Laplace transform takes a function in the time and maps it into a function of frequency. Now, this could be a linear map. What does that mean? That if you have 2 functions, you have a times one plus b times another, it's like vectors, that it should map it to a times the Laplace transform of the first plus b times the Laplace transform of the second. All right? Then you say an operator is linear when it does this. Okay? Now, it's really easily checked mathematically, just plug all this stuff in an integral. But now let's stop a moment and say what this means. So you have 2 cash flows. right? Just think of it. I'm just receiving one cash flow, I'm receiving another one, right? And suppose A and B are 1. What will be my total cash flow then? Well, that's the sum of those two, right? So if I look at the present value of 1 and then the present value of the other cash flow, wouldn't it make sense that the present value is the sum of those present values? Of course it would. In fact, that's the whole reason they used present values, because if it didn't, then what's the point of thinking what the net present value of anything is? Because if you add something to it, you'll have to start all over again, right? So talking about the value of things, value is an additive property. So if I have value of one home and the value of another home, together the value is simply the sum, right? That's the idea of value, that it's additive. Now, if the only reason a home has value is because you can get a stream of rent from it, okay, then it should make sense that if that is additive, that our notional value has that same additivity as the stream of rent, because they're going to be additives to begin with, because they're just two velocities that I'm adding, all right? Okay. So you can check this linearity by going through the integral sign and just going and saying, oh, it's a linear operator. And now the superposition principle applies, and then you go on, and it seems something magic. And then we always ask students, now, why does this work? And what is a linear system? And they're totally confused, okay? And then all they have to say is, well, the superposition principle. And then you'll have exams, and they'll just, they slowly disappear. And then later on, they find that that's all they have to say. And you get confused what a linear system is, all right? But that's what you want. You want the linearity to stay put, okay? So you can add cash flows, therefore you should be able to add present values. You can multiply a cash flow by a number. Instead of $1, I'm getting $5, okay? Today, tomorrow, whatever, right? Okay, well, then I should be able to multiply the present value, of course, And so this thing is obvious. And it's a little bit, in the economic interpretation, it's just built in. Why else would you do it? It will make no sense to think of values if they're not additive. All right? Okay? All right. So this thing looks innocuous, but it trips up every student, okay? So let it sink in that if value is additive, then then the cash flows are additive inversely, right? So the Laplace transform is a linear operator, right? So the space of cash flows is a linear vector space, gets mapped into another linear vector space. That's the space of present value functions, okay? Boom. Then you can do something, and it's called duration. Now, a lot of you don't know what this is, and I don't want to give a whole lecture on what duration is, but you have two types of duration. One is Macaulay duration, and the other is what's called modified duration, I believe, right? So, Brett, you probably know this a little bit better. But what they do when they do duration, this is what people in the bond market do. So they have a bond, and this bond is going to be repaid at a certain time in the future. So they want to see how much risk there is, okay? So what they do is they take the payment and they multiply it by the time it takes to get the payment. So you get kind of a leverage arm of time. So you see how time is leveraging your payment, right? This is what they call Macaulay duration. And they integrate this thing out, and then they start calculating it, okay? So if you go to Investopedia and they try to explain it, they'll do something like this with a lever and all over, all right? Kind of complicated, but now look at what in this Laplace transform table, what happens here. So what are you doing here? You're taking the derivative in the frequency domain. What does that mean? Okay, if this is the value of your cash flow, then you can ask yourself what happens to that value if I change the discount rate a little bit. Suppose I'm going to discount a little faster. Now, what's going to happen to the value? I want to know, because I don't know. Maybe this thing is very interest rate sensitive, so if interest rates move, I want to know how my value changes, right? That's just this derivative, okay? So this is very important for a bond trader because these bonds have certain values. They go to the Federal Reserve or the ECB. They ask what the interest rate is. They use it to discount it. And nowadays it's 0, but whatever, right? Huh? But then the Federal Reserve may change the interest rates, or the ECB may lower it or heighten it. Then they want to know what happens to these values of these bonds, right? So they take the derivative. They call this the modified duration. Right? They put a minus sign in front of it, and it's exactly equal to this, the time weighting of the force. Okay? So this is an equation. If even the engineers can steer this forever, and I don't even know when to use it, but it goes quite high up in the Laplace transform table, so that multiplying by t is differentiating. Again, in finance, you have an easy interpretation. Okay? Immediately see this. You can take further derivatives. This is called convexity. And they have more, and they go nuts, and they get confused, right? It's just looking at, changing this leverage. All right? So fully discussing this will take us on a whole course on how you treat bonds and duration, and we're going to leave that to Britt to tell us about. But I just want to put it there for you so you can see how useful this interpretation is, really, this economic interpretation, all right? And how you can just clarify everything. You can just go down, right? Now, here's another one that everybody knows, okay? So this is what Rumer already said. If I take a derivative, this dot is a time derivative in the time domain, I multiply by s in the frequency domain, right? Okay? Now, and here's the integral. So, what's cool about that? All right. Now, what if you have the present value? So that's an amount of money you may think is equivalent to this, right? So this thing is for cash flows is measured in dollars, right? So this will be some form of capital, if you want, financial capital. Right? That's everything that your cash flow is worth for now. Now, suppose I take that and I multiply that by the discount rate. Okay? In this sense, it's also called the internal and this is used in capital budgeting. So you say, all right, so I can, so I have all these projects, and then I do this, and I get this in return, and I get that and that in return. You know what? That's way too complicated to keep track of exactly how these returns are changing here that I'm getting, right? Instead, I bring everything to the future, and I multiply it by one number, the internal rate of return, all right? And then I get an assessment of what the value of this project is going to be, all right? So there you go. It's just a simple thing. So you can say, for instance, in yours' application, he has the value of houses, and you have the value of a house. And then what does the government say? The Dutch government, they are very good at doing this kind of stuff. They'll say, well, you have this house, and you're not making any payments because it's yours, right? So, that's kind of unfair to the people who do have to make payments. So we're going to pretend that you are enjoying this house at a rate that's equal to what we'll call it forfaitaire rendement, okay? And that's Dutch. But you can say that's the imputed interest. So we're kind of thinking that somewhere in there, internally, you are getting all this wonderful stuff out of this value of this house. I multiplied by 3, what is the rate for forfaitaire rendement? 3% or 5%? I don't know. Veel lager, hè? I think it's half a percent. Huh? So they said S equal to a half. 0.0. Sorry, yeah. Whatever, 5%. Huh? Right? I don't know, some number. I remember in the old days it was set to 4.5, and then you had to pay tax on 33% of 4.5, and it's kind of complicated, right?
Now, these are two different things. Do you mean the capital tax in box 3, or do you mean the forfeiture?
In box 3, the government assumes that this is 4.5%, I think.
Yeah, 4%.
4%. Yeah, and then you will be taxed 30% on the 4%. So they assume that this is what your house is, the value is this. They'll assume you make 4% on that, right?
I thought you meant in
Yeah.
box 1, and there you've got your own house forfeit.
Oh.
That one is even lower.
I see, yeah.
But,
I see.
It's already multiplied with.
Yeah, well, because you.
But with 10% or something.
Right.
That makes the half.
Right. Anyway, this is what they do. Well, see what they're doing. They're just multiplying present value by S, right? So they're just calculating, how your wants are being discounted over time, right? How it's changing over time. Huh? Okay, they'll get some other Laplace transform here, and this is precisely the Laplace transform of the change of the economic force. Okay, so that's your forfeiture income, your imputed income, right? So this is actually in dollars per day or year, I would say, right? This is in dollars. This is 1 over years. So this is what they call the imputed income. So this is the imputed income, and this is the internal rate of return or imputed interest or forfeiture. Rendement, interest is rendement, and forfeiture is imputed, okay? So there you go. This is just, you write it a little bit differently, all right? Huh? Yeah, you take the imputed income, divide by S, and you get the value. All right? This is why it's so convenient. It's not only convenient for the control theory, it's also very convenient for the taxman and for the investor who talks about an internal rate of return on an investment for so many years, okay? And then he assesses the value of this. This is what PwC does when they are, doing the discounted cash flow method, all right? So this is important to let it sink in. This is the most important property for a control engineer, and it's also what makes this whole calculus of values work. How the discounted cash flow method, that's called the DCF method, works, how the taxman works, and this. Currently, I'm talking to people. We're thinking at the tax authorities and thinking of, box 3 is in the frequency domain and box 1 and 2 are in the time domain. It's a little strange, right? Huh? What? Except for the exactly. So there's a very strange. So we're all excited about Joris's thesis that is addressing these things in the housing market. And how the taxation goes, how the value goes, and all of this, okay?
So is box 3 looking at your vermogen?
Yeah, but, so it looks at the value, income, time domain, and this looks at the value of your assets, okay? And here, they'll tax you on this income here, which is the Laplace transform of the flux of, the rate, the change of your economic force, all right? And somehow they make you pay this in cash. This is where the problem is. Huh? So if they didn't let you pay it in cash, you would just accrue it, and it will be there, and then when it goes down, you can take it off, and then when you sell it, you convert it to cash or not, and then you would pay the tax. This is how it's done in the United States, for instance, and I believe also in Germany. This is how they do it. But in the United States, I'm sure, because I've lived there long enough and filled away enough tax forms to know this. So you pay capital gains tax. So only when you sell it do you pay money. You don't just pay something in between, So this is the rub, because if you make people do that, two things are going to happen. Either they don't have the cash, since it's not in the time domain, and this happens, so people, then they have to make a deal, they got to sort it out. Because they can't let the go bankrupt, and And so this happened with people when they had large houses, you know, so they would make all this income and then they would have to pay it and they don't have the money. Then it's not their fault this house is worth so much, right? Huh? This was how it worked before in the Netherlands, that vermogensbelasting. Huh? And then they changed it, they adapted it. But in the United States, or the other option is that the returns are way higher. So then you're just laughing all the way to the bank. These people are earning tons of money and they hardly pay tax on it, you know. So you're always wrong. Except in one lucky case where you're right, and the moment they write the law is precisely that one lucky moment that the two things happen to coincide, you know, and then it diverges and the whole thing starts creaking. Okay? Again, you see how useful it is, this type of analysis, and you see how the tools we have to do that, economists don't have, namely the Laplace transform, helps you to just kind of clean up this whole mess. All right? Conceptually, at least. All right? You also have a trend. So you know a trend, you know, you can go something like this, yeah? And then you may have your signal is doing whatever, and then you add this trend to it, you multiply it, so it's going to do something like this, right? Huh? All right, so you take this, and then you have to multiply, you know, huh? Oh my God, this should be a T. Thank you. I thought I fixed that. There must have been another error somewhere. This should be a T. Thank you. This is the time domain. I mean, how could I have written an S here? It's ridiculous. Huh? Where?
Linearity. Discount. W.
Oh, Jesus.
It's fine.
Thank you. You write these things and you never see the error anymore, right? It's exactly what you guys have when you write your thesis. Huh? Yeah. Now somebody comes and says, hey, what is this? Ooh. Huh? So I get a trend, and all you need to do is subtract it from your internal rate of return, right? Sure. Yeah, so if you have a signal and it's you're discounting it, but now that same signal is trending up, you might as well, you know, just reduce the trend by the amount of the discount rate, and then you're just fine, right? That's precisely what this thing is doing. Huh? So what do they call this? Like a frequency shift or something? Huh? I think that's the frequency shift, huh? Because you're shifting the frequency. You know, it really is just an adjustment of the internal rate because you have an added trend here. Huh? So detrending, you can just do this. So by detrending, you just get rid of this. You just start working with that, and all you have to do, and simple. Then you can have, say you have some kind of cash flow, but it starts, instead of now, it starts some moment tau in the future. So you make some contract, and you say, all right, I'll deliver the, you know, I'll buy it as of the date. So you buy a bond future, right? They're called bond futures. So you buy cash flow in the future. And then, of course, you have to take the entire present value and then discount it back to the now, right? Because that thing is now not starting at zero, where you can get, you know, but the zero is now has to be entirely discounted back over a period tau.
You're discounting twice.
Pardon?
So you're discounting twice.
Yeah, so you're first internally discounting the flow, and then you take the whole flow and you view it as a single payment at time tau, and that you got to bring to the present, right? That's what you do. I mean, that's what an accountant would do or something, you know. I mean, you would write down this rule of the Laplace transform, but somebody who doesn't know that, that's precisely what he would be calculating, right? So that's my point here. So this table, I mean, you have to remember it, but if you just think of it as a present value, the whole thing becomes intuitive, right? Huh? And that's the point I'm trying to make here. So I'd like to see some nodding heads. I saw one or two, that this is coming across, You can take any one of these, and rather than, because I looked at my books and they always went, okay, let's go and prove it, integration by parts, boom, they're very clever, right? And there he gets the result, right? So
something that's nice to see is that there's a lot of symmetry, right? So for example, for duration, you have derivative of time domain and term domain. So time domain.
right.
And if IRR is exactly the opposite, so the time domain.
Exactly. Yeah.
Those two are also exactly symmetric.
That's right.
Yeah. So.
Yeah, that's another fun thing to see. So you see, this is the thing. Rumor just said, well, I do it because it makes some things easy. It makes it easier. But some things it makes harder, right? Right? Because that's exactly what Emil is pointing out. It's just switching the roles of multiplying by t and taking derivatives, for instance. But here it does the opposite, right? Switching the roles of multiplying and taking the derivative. So if you're taking a lot of derivatives in the time domain, it's really great to be in the frequency domain, right? And you don't want to take derivatives. If you're taking a lot of derivatives in the frequency domain, maybe you want to go back to the time domain and multiply to have it algebraically, although people seem to be pretty cool doing this in finance, okay? Well, in the sense that Macaulay duration was what they had first, and then later they kind of switched to this. So maybe this is more intuitive, Yeah? So,
You said ERR for imputed return.
This is the term they use in capital budgeting, Everybody uses something else.
Yeah, but this isn't internal rate of return.
This is the internal rate of return. It's just what they use in capital budgeting. That would correspond to this. You see? But you probably wouldn't use that in your research. I would call this the imputed rate of return, or the imputed return, right?
Yeah, because there I would use the imputed rate of return, and for ERR I would say that for internal rate of return it would be the argument of the where the net present value is 0. So the rate at which the net present value is 0. The discount rate.
This thing?
No.
Oh.
So there and then the argument. So for which S this equality holds.
So S such that this, and then you call that the internal rate of return. S is the internal rate of return. Right. So I guess what I was thinking was they try to monkey around with this internal rate of return. This is a 0. We will see later when I talk about poles and zeros, right? Mm-hmm. So in a sense, they're varying it, right? Mm-hmm. And they're trying to vary it so they get the 0 here, right?
Yeah.
So you could also interpret their whole capital budgeting as monkeying around with that thing and seeing where their zeros or their poles are if they took at the inverse.
Yeah, exactly.
You see?
So, but then it's slightly different.
Yeah, you're right.
So,
yeah, I just made some suggestive, This is just suggestions, that I came up with when I was preparing the slide, I just put a little example in my head and I try to work it out, and I guess I had in my head this capital budgeting thing, and then we started talking more about your problem, and then it was a little confusing, right? But I think you are right in using the terms the way you do. You're pretty sharp on this.
I'm long and hard on this.
No, I mean, that shows, and it shows. I mean, you can work long and hard and nothing shows, So a lot of people have that feeling too. Let me move on. I want to do some interesting stuff. So my time is running out. The problem is, this is pretty interesting, so you can talk about this forever, actually. I just find new things. It's fun. Huh? All right, I put this into, there are these two theorems, the final value theorem and the initial value theorem. Let's not spend too much time on it, but they really correspond to what economists call the long run and the short run, right? So what is this thing? You just have your economic want or whatever it is, right? And you look at it in the steady state, now way out in the future, right? Way out in the future, okay? Now, how do you get that? Well, you're going to look at the imputed income here, okay, but way out where the discount rate is almost zero, because if the discount rate is high, you're going to lose everything in the future, okay? So you're going to let the future count as much as possible, and then you're going to look at the changes of your capital due to the, not the future, but the low, so that the discount rate is low, all right? Huh? So it's kind of, huh?
What's the point of this?
Well, the point is that these things are the same, right? And this is called the final value theorem.
When would you use it in an economic sense?
Yeah.
Well, you would, because you're in the frequency domain, so you're talking about valuations, you may say, well, if I look at this, what is this? Well, really, it's the steady state value of my, now. Eh? So you get this connection where you can say, you can write this equation, which a lot of people write. They take something in the frequency domain. This has the same units, right? So the units correspond, right? Because I'm taking this as I'm taking unit of time out and I'm multiplying again, right? Huh? Right? So you would want to say stuff like this. This is what people always do when they design this box 3 and all these things. They want to take something in the frequency domain and set it equal to something in the time domain, right? But the point you got to see is that can only be done when you look at the steady state value. So that's the what economists would call the equilibrium value of the force. So it's going on, and then maybe it will die out. And at that point, you can just switch to the frequency domain and say it's this, but I want to discount at really low levels, right? So it's also one of the things that works for you, and when you look at the book, right? So the book, you can discount at low levels, and you can set these things equal, right? And this one does the opposite, right? So I approach T, I approach it from the right, and I get, what do I get? I get the payment at time is 0, right? Huh? So that's a payment that's immediate. Now, how would I get that in the frequency domain? Well, if I take this thing and I just discount the hell out of it, right? So this thing will drop off immediately. So I only will count the first payment, And then I look at the return I get on that first little payment, and there I have it, right? So this will just give me two conditions under which I may equate time domain and frequency domain, There may be more conditions, right? So this may be what the Dutch taxman is doing. So they're saying, look, prices are just at this level, the steady state level, right? Huh? And so there we are. So this is the limit. So this is what the prices are. And therefore, I'm going to tax people this, right? Huh? So, fine. Except they may not be in steady state level. They may move around, right? And then the whole thing goes pear-shaped, right? Does that answer your question? When you would, you asked the question, when you would ever, does that answer your question? Yeah. Yeah. So I think it's, I mean, you learn this stuff, right? Huh? Did you ever use it in engineering?
No. Sometimes.
Something, yeah.
Twice.
Twice. Yeah.
Yeah, for steady states values.
Yeah. Steady state.
Oh.
And also steady state errors. It's like
Yeah.
you see like system type, for example. That's
Right.
also from the final value theorem. It's,
Right.
You know, how many integrators it has.
Yeah.
Yeah, exactly.
But then you would need an absolute.
I don't know. I mean, these things are just generally valid, you know. As long as I didn't make a copying error, this is just what it is. But I think Emil's point is very clear. You use it all the time, especially for the steady state value. Why would you use it in economics for a steady state price or a steady state economic force? You know, and you can get those by looking at the frequency domain. It's just that one happy coincidence where everybody always latches onto and then gets into trouble when this thing happens not to be when we happen not to be in the steady state. Huh? Okay. And this thing you can also use, this one is a little bit more trivial in the sense that, of course, the value of the payment here, you would get it by discounting really fast, you know, and then you just find that, you know, because all the future doesn't weigh anymore, right? Maybe little as useful, but maybe not. Maybe this is what they do. They say, well, right now, this is the case, you know, so... Huh? So we make this really small, right? We don't make it infinity, and then we can just pretend that this is the case and equate these time and frequency domain. All right. But again, notice how, with the interpretation, this whole thing comes alive, you know, and you can use it in your theses. You can do stuff with it. You can get good economic results and impress your committee with the final value theorem and how you understand it, and you know, and they'll be impressed. Okay, so now I have 15 minutes. I want to talk about a topic that's very dear to my heart. Why a pole is called a pole, all right? So we all know that, huh? Do you know why a pole is called a pole?
I said something really. I said because he's from Poland.
He's from Poland. There's an old joke. You know, there's an old joke. Yeah, so why Polish Airlines? Why did the Polish Airlines airliner crash?
Why?
Because all the poles, they went into the right half of the plane, all right? Boom, huh?
Yeah.
So that's a joke. Some people make an attempt and they say, well, they think about it like 10 poles sticking out on the Laplace transform. Huh? That's not right either.
Is that not? Because
That's
I
wrong.
always assumed that was the case, but
No, it's a real pole. It's a pole, yeah, it's the North Pole. Okay? Now, what I want, huh? And we have a problem, you know, because what I want to do is show you why it's the North Pole. All right? This is kind of a fun thing for me because it changes your perspective about what the S-plane looks like, what the topography and the geometry is of the X-plane. And this will be very beneficial to you. Huh? Because in the S-plane, you'll have poles running off to infinity, and we talk like this, oh, the pole ran off to infinity, I got a zero in infinity and all of this, you know? And then you go like, okay, well, where is that then? Well, I don't know, right? Huh? And they're always at infinity, and why is there not a whole circle at infinity? Or at least two, minus infinity and plus infinity? Nobody knows, right? It's just the pole at infinity. And the problem lies here in these... Yeah, it's like here, this thing, right? So if this were 1, then you would have this whole thing will be exploding like crazy at 0, right? So, but I'll come to that in the next thing. Let's first tell you how this is fixed. If you are now, the guys who developed this control, they knew something. They knew all this math of holomorphic functions and all of this, and they would know why this is called a pole, and that's how they called it this way. But I just want to do this first. And we're going to do it only for real numbers. So here I drew an axis, the blue axis, and this has your discount rate, right? So it is S. These are the positive values, and these are the negative values of S, okay? So you think of this as the S-plane, but only the real axis, okay? Then where would infinity be? It will be, right, minus infinity will be here, and plus infinity will be way out there, right? Huh? Okay? So far, so good, right? Now, the problem is I want to plot these things at infinity. So, you know, which you always want to do when you're in the S-plane. So you can't really do that when it's a straight line, right? But this is a device that allows you to do that nevertheless. And what I'm going to do is I'm going to take this line and I'm going to wrap it around a circle. So I'm going to take this point, move it over there. I'm going to take this thing, move it over there. This thing will move over there, and this part will move over there, and this part will move over here. All right? Okay? So I'll have the same x-axis, but it will go from plus infinity to 0 to minus infinity here. So plus infinity and minus infinity will be the same. I'm going to tie them up. Okay?
One-point compactification.
This is called the one-point compactification. Now, how would you do that, right? Huh? You would do that through stereographic projection. So what I do is I imagine a little light here, right? Or maybe my eye is here. And I'm looking at the points in this plane, you know, as light is shining through this thing. So these are rays of light. So I'm take this point here, and I'm going to map it over there. Okay? I'm going to take this point, and I'm going to map it over there, this point over there, this point over there, and this point over there. All right? Okay? So that will work. But what happens to when I go further out? I'll go here, 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 here. And at a certain point, when I'm infinity, then it gets mapped over there. Okay? Simple. It's called stereographic projection. You can think of this as the Earth, you know, and you can think of this as the night sky. You know, you see all these things out there, and then stars, and then, you know, you see this is the celestial dome, and then you just project them, you know, from some plane out there, you project them down. Yeah? Or you can hang up your dome, a globe of the Earth, in your room with a light in it, and it will project down on a plane, and you will see the whole Earth kind of projected, you know, now on a plane. But we're doing the opposite. We're taking something on the plane and putting it back. Now, the advantage of this is, as Emil said, is the one-point compactification. So this thing is a compact manifold, okay? Meaning it doesn't have any holes in it. This thing has a hole, right? You just roll off on this side, you know? This is what people used to think, that the Earth was flat. So what's going to happen when I reach infinity? Well, the point is it wasn't. When you reach this infinity, you're just over here, okay? In this stereographic map, okay? Now, this thing is called the North Pole, and this is called the South Pole. So you'll see that infinity is at the North Pole, right? Simple. Anybody can understand this. Everybody sees this, huh? Of course, you do a lot of stretching, right? This thing gets all crunched in here, right? And this thing gets a little bit stretched out. Yeah? Okay? Okay. Huh? Right? But think of it, think the S-plane, just say, up to now, I thought it was flat. Like some people thought the Earth was flat. It really isn't. It's really round. Okay? And it's going to solve a lot of my problems. I'm not going to roll off anymore and this and that. Now, how does that work? Let's go to the next slide. So now I take the Laplace transform. So I calculate a present value, right? So what is this function? It takes a value S, a discount rate, right? Somewhere on the real numbers, and it maps them on another line, which is the present value, right? Okay? So blue to blue. Now, what I'm going to do is I'm going to take this line S and I'm going to stereographically project it on this sphere. And I'm going to take this blue line, I'm going to stereographically project it on that sphere, right? I can do that. And then it becomes a map, not from the blue line to the blue line, but from the black circle to the other black circle. Cool? All right? So, and what's nice about this map is we can see the entire action. We don't have to like worry about what happens when we roll off our graph, because we've got everything in the graph, albeit a little bit scrunched up, right? Now, let's look at a function we have, 1 over s, for instance. Okay? Now, if you take the point 1, where does this go? It goes to 1, right? Okay? Minus 1 goes to minus 1. So the equator, this will stay the same, right? But what about the point 0? Where does that go to?
Infinity.
Yeah, 1 divided by 0. So you go very close, and then you'll see it goes over there, right? And what about infinity? That one goes to 0, right? Okay, simple. So what this thing does, this map, it just flips this around. Ooh, huh? You see that? Actually, if you work it out, that's all it does. This map is called an inversion, and it just inverts it. So you can think of this as a mirror, boom, boom, that's all that this map does. All right? Now, if this were a signal, okay, then where's the pole of this thing? Huh? Well, it's at the point at which it becomes infinity, so that's at 0, right? So we would say it's got one pole at 0, right? That's also only saying I took 0, which was here, and then mapped it here, and then it just moved to the North Pole, right? So that's where the word pole comes from. It just is the point that you map to the North Pole, okay? You don't have to do 0, you can do this map, right? You can sort out where 1 goes to a half or something, right? And it must be here somewhere. But what's interesting to see is where s is minus 1 goes to. So that's this one. And this thing goes through infinity, right? I mean, plug it in, right? So this one has a pole at minus 1. Okay? You can look at more maps. Huh? Anything you like. You can have S plus A, S plus B, all these. Huh? A point is really, this is one way to look at it, and you'll see that this pole is not really shooting off to infinity if you're slowly increasing it. It's just kind of turning or flipping or this, okay? Huh? All right? That's the origin of the word pole. It's just that in the transform domain, this thing shows up at the North Pole, you know now, huh? And then that is a pole, since in the value, it's infinitely value. By the way, why is what's the economic meaning of 1 over s having a pole at 0? We'll end the lecture with that. Well, let me just get to this thing. I'll end the lecture with this, and we'll look at a perpetuity. A perpetuity is something that gives you $1 just over all of time, all right? Okay? The value of this is 1 over the discount rate, okay? So if the discount rate is 10%, 1 over 10%, so what is that? 10. Huh? So the thing is worth $10. If the discount rate is 100%, you're not doing very good. 1 divided by minus, no, sorry. Huh? But now suppose, okay, you could go on like that, right? Huh? You can calculate these things for a different discount rate. Now suppose the discount rate is 0. What are you effectively doing? Well, your value is the integral of whatever it is times e to the 0 times t dt, right? This is just 1. So you're integrating your force over from 0 to infinity. Well, what is this? That's the unit step. So how much are you going to accumulate? It's never going to stop, okay? This thing is going to blow up. This thing has infinite value to you because you're going to have an infinite stream of payments and you're not discounting anything. So this whole thing is not converging anymore, all right? So these things don't make any sense, really, because nobody would give you such a thing if discount rate were at 0, right? Huh? Because it's worth an infinite amount. So the Laplace transform, of course, diverges at that point, okay? And if you increase the interest rate further, you get nonsense, you know. So out of the region of convergence of your Laplace transform, you can plug it in, but you're going to get nonsense, all right? Huh? Okay? All that's happening is you're right at the pole here, all right? Okay? So I want to stop the lecture here, and you'll see that with this idea of a pole, and it's kind of a little preview why this thing is equal to that, and how you can think through all these other ones is going to work, as long as you know what a pole is and a 0 is. Huh? Because, of course, the 0 is precisely the opposite. That's the thing that is mapping to the South Pole. Huh? Now, the question is, does the North Pole always map to another North Pole and the South Pole to the South Pole? Maybe, maybe not, right? And sometimes they get lost, and then you'll have to go to the complex domain. We'll go to the Riemann sphere, and it will get more complicated. All right? So with this, I'd like to end this lecture, and we'll continue the subject next week.